Hi, today we will see another chapter on fluid dynamics. This will be the part 2 for chapter 4. Okay, we will study about Bernoullis equation. Okay, so Bernoullis equation is found by Daniel Bernoulli in year 1700 to 1782 years. Okay, so it's almost like 400 years back. So when he was investigating the fluid flow. Okay, so he is a merchant, he is a doctor, he is a mathematician, and he investigated the force present in the moving fluid. Okay, so previously we have seen about the fluid which is static. So we are now doing some investigation on a moving fluid. Okay, and out of his experiments, he has come up with equation called Bernoullis equation. So Bernoullis equation will be very useful when we want to find some parameters related to moving, especially the pressure at a particular point. Okay, so we will see how Bernoullis equation will help us in determining the fluid flow. Okay, some understanding on Bernoullis equation. The Bernoullis equation is an approximate relation between pressure, velocity, and elevation. Okay, there are three things that are involved in the equation. It will have three parts. So the first part will be dealing with pressure. Okay, and second will be related to velocity and also the elevation, meaning different height. And it has some conditions to be met before we can use. So it only can be used in a region where it has a steady incompressible flow. Okay? So if you are having a flow which is not steady and is compressible, then you cannot use Bernoulli's equation. So that's the limitation of the equation. Okay, so Bernoulli's equation is typically useful in flow regions outside the boundary layer. Okay, so normally we can see, yeah, you have two. Okay, so this is a fluid flow. Okay, we can see where the Bernoulli's equation will be valid. So where there is a steady incompressible flow. Okay, and here it's not a steady, so you cannot use Bernoulli's equation in this particular region. Okay, so conservation of linear momentum principle, or we call it as a Newton's second law. Okay, so it is used to derive the Bernoulli's equation. Okay, it's only valid in the inviscid region. So inviscid region is a place where no friction. Friction is very steady, and also you you can neglect the frictional force in that particular area. Okay, so the limitation of the use of Bernoulli's equation, something that I discussed earlier. So you must have steady flow. Okay, the fluid flow must have a constant rate. Okay, so if it's changing, you cannot use. Okay, and it's incompressible flow. So meaning the density is constant throughout the flow. Okay, if you are measuring between point 1 to point 2, so you must have a constant density and it's not compressible. Okay, so the specific weight of the fluid is assumed to be same in the two sections. Okay, and frictionless, non-viscous, inviscid flow. Okay, flow which is very relaxed and you don't have any additional forces acting on that particular flow. Okay. Okay, there can be no mechanical device. So if your flow is connected to a pump, which will increase the speed, and you have a turbine, you have a fan, or you have other types of machines or impeller, in order to destroy or affect the flow, then you cannot use it. Okay, so whichever uh, devices that can add energy or remove energy from the system. So because we want the equation, for the equation to be valid, you need to have the total energy of the fluid to be constant. Okay, so there can be no heat transfer in and out. Okay, so there are few conditions that you need to understand. Okay, so flow along the streamline. The Bernoullis equation is applicable along the streamline. Okay, not condition or to different streamline. However, when a region of a flow is irrotational, okay, and there is a negligibly small vorticity in the flow field, the Bernoullis equation become applicable across the streamline. Okay, so you can see here uh, the flow is steady and is irrotational, meaning it's not rotating. It's not rotating. The fluid particles do not spin as they move. Okay, if something that is moving, so that is actually a cause of turbulence. Okay, then we cannot consider it. Okay, so this is the Bernoullis equation. We will see how it is derived. Okay, so derivation of the Bernoullis equation. So you take this particular movement or particular surface in a streamline. So you have a streamline, okay, from here to from bottom to up. So this is plane over distance and height. Okay, so you have a gravitational field opposing the moving downwards. Okay, so we are using in the derivation we are using Newton's second law, okay, in the s direction. Okay, and we are using force S equals to MAS. Okay, so if you derive, so I'm not really talking about the derivations, it's more on the integration and differentiation. Okay, so you can derive, and when you integrate the final product, you will get the final equation. So this is the Bernoullis equation. So as long you fulfill all the conditions given, then you can use this equation. So you have three parts. You have three parts in the equation. So the first part is pressure over density. Then it is actually showing the flow energy because it's related to the pressure and also density. And the second part is the kinetic energy. So it is derived from half mv square. This equation for kinetic energy. And you have a potential energy. So it's related to the I, and it is a constant along a streamline. So based on this, so you can come up with the final equation. Okay, that the equation that we have seen earlier is only for one particular point. So if you want to use the Bernoullis equation to measure between point 1 and point 2, then you would need to combine it. Okay, so you can see here, as stated above, the Bernoulli equation applies to condition along a streamline. So we can apply it between 2 points. So you have point 1 and you have point 2. Okay, so you want to measure the flow. You want to measure the parameters involved in this. So when you have 2 points in a streamline which meet all the condition, then you can say that 2 points joined by a streamline, the total energy per unit mass at 1. The total energy at 1 equals to total energy at 2. Okay? And you can say total 8 at 1. So this is the equation we saw earlier. So this equation at 1 equals to the similar equation at point 2. So you have point 1 and point 2. P1 is indicating pressure at point 1, P2 is indicating the pressure at point 2. So similar. Okay, or you can say the total pressure at 1 equals to total pressure at 2. Okay, so that's what you can say. So based on this condition, you can get the final version that you can use in your calculations. Okay, so it's saying, so you times all this equation with rho g, okay, in order to cancel out. So you times all the components with rho g, so the density and gravity. So you can get the final version, Okay, so P1 plus rho V1 square over 2 plus rho GZ1 equals to uh, P2 plus rho V2 square over 2 plus rho GZ2. Okay, so the first part is indicating the static pressure, a pressure when the fluid is not in motion. Yeah, so you are just taking the instantaneous pressure, so meaning pressure at that particular point at the particular time. P1, then you have a dynamic pressure. Okay, the pressure rise with when fluid in motion. So when the fluid started to move, then you can have a dynamic pressure. Then you have one more, we call it as hydrostatic pressure. So it's related to the weight and also the height. So you have for both points. So the practical use of the Bernoullis equation. See, the Bernoullis equation is often combined with the continuity equation to find velocities and pressures at points in the flow connected by the streamline. Okay, initially previously we have studied about the continuity equation. Okay, the conservation of mass, okay, in a control volume. Okay, now we are combining it. So Bernoulli's equation alone uh, might not be useful unless you use together with continuity equation. Okay, so you want to find the velocities and pressure at particular point in a streamline, then you can combine with continuity equation. Okay, so for example, you have a system here. So you have 2 points, section 1 and section 2. Section 1 is having its particular velocity and also pressure. So section 2 also having its particular velocity and pressure. So the example is asking you to find the pressure and velocity when contracting and expanding pipe in the expanding pipe. Okay, based on this, okay, so these are the parameters given. So we will see in this example how we can use this Bernoulli's equation with continuity equation to find values. Okay, so these are the values that is given. Okay, a fluid with a density of 960 kilogram per meter cube is flowing steadily through the above tube. Here section diameter are d1, so all the values of diameters are given. You can use it to find the area. Okay, and pressure P1 equals to 200. Okay, so this is the equation, final equation. So you just need to replace the values inside. Okay, the velocity u1 equals to 5 meter per second. The tube is horizontal. Yeah, horizontal meaning is at the same height. Same height. So the z1, z is the height, different height. Okay, so z1 equals to z2. So the height of 1 and 2 are the same. Okay, then you are applying it to the equation you derive. Okay, so this is the derived equation. So this is before you times it, rho g. Okay, then once you already rearrange, you already times it rho g, and then you will get something like this. Yeah, after you reduce, you substitute all. So since z1 equals to z2, you can cancel out and you rearrange, you will get this final form of formula. So from here you can see, you can find pressure 2 by including pressure 1 plus rho over 2, the speed 1 square minus speed 2 square. So based on that, you can find the value of E. Okay, so when you solve, okay, how you can use the continuity equation. So the continuity equation you are using a1 u1 equals to a2 u2. So that is from the continuity equation we studied before this. Okay, so you rearrange, you can find a1 u1 over a2. Okay, so this is one of the equation to use the diameter. Okay, diameter 1 over diameter 2 square times with u1. Okay, so you will get 7.8125 meter per second. So as your U2. Okay, so based on this, you can calculate. You just substitute in the previous equation for P2. So is given 200,000 minus the remaining values after you replace U2 inside the previous formula. Then at the end you can get 182.7 kilonewton per meter square. So that's the pressure at P2. So this is how we can use both Bernoullis equation and also continuity equation in order to form partnership in solving uh, parameters. Okay, so using this continuity equation, you can and the combination with Bernoullis equation, you can find the pressures, you can find the velocities in a steady flow. Okay, and also you can find and I the different I if Z1 not same with Z2. Okay, so with that, so we come to the end of chapter 4, part 2. So you can answer the question given. It's a very short recording today. Okay, so I hope you are benefited. Okay, so thank you. We'll see you again. Bye.